Good evening, everyone. Am I audible? Can any one of you just put it on the WhatsApp chat or basically on the chat of YouTube so that I can start? The moment you let me know that I'm audible, I'll start. Just waiting for one more moment. Yeah, good evening, everyone. So I can see all of you. So welcome to this small session of Master Mentor Tips. The basic idea behind these kind of sessions is to ignite that thought process where you start thinking the fundamental way. It is very important for each JE aspirant or Olympiad aspirant to think from the very basics, from the very elementary thinking. So I thought of taking one problem with you and discuss the entire course of this in entirety. Yeah. So I'll begin with reiterating the problem. The problem says that if PA and PB are two tangents to an ellipse from any external point P and S and S dash are the foci of that ellipse, then these two angles that are marked in this diagram, APS dash and BPS, they both are equal. This is what we intend to prove. I would assume that you are all students of class 11th, 12th, those who are taking this particular session of this Master Mentor Tips, and you are basically aware of few things. But despite that, I will go through these three prerequisites one by one, and we will do this also with basic elementary geometry. First is, how do you locate a point on a line such that the sum of its distances from two given fixed points, those points are not on the line, the sum is minimum. Second is, you should be knowing and you should be aware of the fact that sum of distances of any point P on the ellipse from its foci is a constant, and this constant is bigger than the distance between the foci. Third is, basis the first and second. The normal to an ellipse at any point P bisects the angle SPS dash, where SS dash are the foci. We will prove these three one by one quickly with geometry and then take this problem without any x, without any y, no Cartesian coordinate system, only pure Euclidean geometry. I begin with the first one. Let me assume that I have a line and there are 2 points not situated on the line. I can imagine a line and 2 points, maybe A and B. Case 1, if I imagine both the points on the either side of the line, how do you locate a point P on the line such that sum of the distances is a constant? So what we generally look into such problems is that we deal with something called as triangle inequality. Had there been any other point P on this particular line, the one which is given to me, and I have taken that, then this PA plus PB is definitely greater than AB, and equality holds if P lies on the line itself, line segment AB. So this way we locate a point P, no x, no y, pure geometry. The logic concept behind this is called as triangle inequality. Sum of two sides in a triangle would always be greater than the third side, and the equality holds if the triangle is not formed. I take up another situation. Maybe there can be a situation when both your points A and B are not lying on the same side of the line, and still you are asked about PA plus PB minimum. Now the challenge is you cannot say that a triangle inequality is formed. So generally what we do in such cases, we start taking clue or help from concept of images. What is image in two-dimensional geometry? An object and a particular image and the mirror itself. Then the line mirror basically behaves as the perpendicular bisector. So if I look at A and A dash as mirror image of each other, I can comfortably say that whatever is PA is also PA dash. So that would mean finding PA plus PB minimum is as good as finding PA dash plus PB as minimum. Now, if I try to find PA dash plus PB as minimum, this goes back to the situation of the first problem, that A dash and B are on the opposite sides of the line, and hence this particular P will give you a situation when PA plus PB is minimum. Had you taken an image of B as B dash, would not have mattered. By symmetry, both A B dash and B A dash will concur at a point on the line, and that point gives you the distance PA plus PB minimum. So the first prerequisite that you are supposed to know is now done. Let us look into the second one. The second one says sum of distances of 2 points in an ellipse basically is constant. I presume all of you are in class 11th and you know that PS plus PS dash is 2A, and 2A is obviously slightly greater than the distance SS dash. So this basically, although can be done with geometry, but since you are dealing this problem and you are already in class 11, so we would automatically assume this thing that this is known to you. So the second prerequisite that becomes the geometrical definition of an ellipse is also covered, that the sum of distances of P from the foci is a constant, and this constant is bigger than this. We can prove it with geometry, but since we have taken a problem of ellipse, so it is understood that you know this much. Now to the bigger one. The statement says that the normal to an ellipse bisects angle SPS dash. So let us take a line as the axis of ellipse, another line as the another axis of ellipse, and then let me try some ellipse as a diagram. If I look at it and try to make it a bit, yeah, somewhat perfect. So how do I prove that normal bisects the angle? This basically is the best part of this particular geometrical interpretation. I take 2 points S and S dash, the foci of these. I take any random point P on the ellipse, and I know PS plus PS dash is 2A, which basically is constant, and this is for every P on the ellipse. P is on the ellipse. The good thing that you probably did not notice or did not realize is also of importance. PS plus PS dash is definitely bigger than 2A if P is outside the ellipse. Am I right? And is less than 2A if P is inside the ellipse. Now at this point of time, I draw a tangent at P. I draw a normal at P. Let it look like something like a normal. If I am supposed to prove that the angle SPS dash is bisected by the tangent normal at P, then this is sufficient to prove that the exterior angle is bisected by the tangent. If I prove that the exterior angle is bisected by the tangent, automatically we will prove that the interior angle is bisected by the normal. How do I do it? For one moment, just ignore the ellipse. Forget it. There is no ellipse as such. Think of that previous problem, the one we did. A and B are 2 points on the same side of a line. So this is your line, and these two are your points S and S dash lying on the same side of line. How do you locate PA plus PB minimum? How would you find a point P on the line such that PS plus PS dash is minimum? The answer is we would basically draw the image of S about the tangent. Wherever this image goes, say probably S1, when I draw join S dash to S1, that particular point P will give me PS plus PS dash minimum. The same geometrical proposition we did a minute back, that if A and B are two distinct points on the same side of a line, then A dash basically is the image of A and I join A dash with B, I get a point. So I would take an image S1, join S1 to S dash, and I can understand that S dash S1, the length would definitely be equal to 2A because PS plus PS dash was 2A. So by the concept, because this is mirror image, so these two lengths would be equal. But if this becomes the mirror image, how do you realize that it is the line is tangent? Because on the tangent, only P is a point where PS dash plus P is constant, that is 2A. Because that is the only point common to the ellipse as well as the tangent. Apart from this, for every point P on the line, PS plus PS dash is bigger than 2A because those all points are outside the ellipse. Now, considering this logic, this concept, we can assume that means the mirror image when joins with this line at a point, the mirror in itself is basically tangent. And if the mirror is tangent, that means these two triangles are congruent, so these two angles are equal. So that means tangent bisects exterior angle. And if tangent bisects exterior angle, normal is a line perpendicular to it. So, but obviously the normal will bisect the interior angle. We have proved the third proposition. Is everyone clear on this? I would reiterate my statement. I assumed this line to be there, 2 points S and S dash to be there. The point P is moving on this line. Now the moment point P touches the ellipse, PS plus PS dash becomes 2A, and the moment it leaves the ellipse, the tangent, howsoever it is, all other points are outside the ellipse, so PS plus PS dash is bigger than 2A. That means this very P is the P where PS plus PS dash would be minimum if P would have moved on this line, and that can be obtained by joining the mirror image to the other foci. So this gives me two thoughts. One, the tangent bisects the exterior angle, done. The normal bisects the interior angle, done. And this segment S dash S1 is having a length 2A irrespective of P. The image of one focus over the tangent, about the tangent, when joined to the other focus, gives me a constant length 2A. We haven't used anything other than basic elementary Euclidean geometry. Now I will take up the problem for which we are all here. How do we do this particular problem? Ready? Yeah. So considering the same very proposition, what I do is, first I take the mirror image of S about one tangent and S dash about the other tangent. For simplicity, let me call these points as X and Y so that we do not have too many dash, double dash and all to confuse. Now, if X is the mirror image of S dash, can I not comfortably assume that the length Px and PS dash, they both are equal, obviously, because this is the mirror image, so that way they both are equal. At the same time, I have taken a mirror image of S in the other tangent PB. Let me call that as PY. So can I not assume that PY is as good as PS because they are mirror image? Also, simultaneously, we have just studied the fact that if the mirror image of one focus about tangent is drawn, then that image, when joined to the other focus, is collinear and basically with the point of contact the way we did it, and basically the length S dash Y, I'll take it here, S dash Y is 2A. So I can comfortably assume this thing, that the length S dash Y is 2A, because we have just proved that the mirror image, the point of contact and the other focus are basically collinear, and this length is 2A because BS dash plus BS is BS dash plus BY, so it is 2A. So be it for the other tangent also. So that would simply mean that when I join S with X, this particular segment is bound to pass through A. AX would have been equal to AS dash. So I can comfortably assume that the length XS is also 2A. Consider these two triangles PXS 1 and PS dash Y 2. What do you realize? The length PX is equal to PS dash first. The length PY is equal to length PS second. And these two lengths are basically equal to 2A. So that means triangle PXS and these basically are congruent by SSS rule. All three sides are equal. Despite of being congruent, they also do one thing. If you can have a look at this, I'll just draw it for you. If I draw one of the triangles through P and there is another congruent triangle through same P, can I not assume that this triangle, when rotated about P to a particular angle, is the other triangle, that is PS dash Y? Am I okay on this? Everybody clear? So with this particular thing introduced in this picture, I realize that the angle that this triangle has traveled from PY to PS is the same angle that the same triangle has traveled from PS to PY. It has been, just imagine the initial triangle being rotated about P to a certain angle to become PS dash PY. So if this angle rotated was alpha, so of course this angle is alpha, and the angle in question basically by symmetry are half of it because we have taken mirror image. So angle alpha by 2 is angle APS dash, and so is angle BPS. Hence proved. We have not used any Cartesian coordinate working at all at any stage. Do let me know in the YouTube chat box if you have any queries, questions on this. I really love to take up all such problems which basically go with elementary geometry, particularly class 9th 10th level, similar triangles and or a lot of propositions of conic sections can be proved through this. So I would want you all to practice this thing, do it in particular time and again, try your own methods. If you have any queries, question, do apprise us, let us know, give it back on the support numbers that are there on our websites or on the other channels where we can connect with you. But make sure, don't unnecessarily complicate a question. Even the toughest and the best questions of JEE, Olympiad and others can be done with fundamentals like this without even involving hi-fi theorems. I leave you all on this session at this point of time with a question as a homework. Whenever you get time, try it. I will have our next session with you very soon and discuss this very problem. The question says ABCD is a convex quadrilateral. I repeat, ABCD is a convex quadrilateral. I hope you all understand what is a convex quadrilateral. A convex quadrilateral is a quadrilateral in which all the angles are less than 180. This kind of quadrilateral would not be termed as convex quadrilateral. The diagonals intersect at a point P. The diagonals of the quadrilateral intersect at a point, say P, some point P. Consider an ellipse E1 whose foci are A and B, and the ellipse is passing through P. There can be some ellipse. Consider another ellipse whose foci are C and D and is also passing through P, somewhat like this. It may appear that they can intersect at two distinct points P and Q. P, definitely they are a common point because they both are passing through it, but it may appear that they can have 2 points of intersection around P, and it may also be possible that they both touch each other externally at P. You have to prove that if this was ellipse E1, this was ellipse E2, E1 and E2 touch each other, of course, as per the diagram, externally. This is for today. Next week, again, same time, we will have another session of mastermind, master mentor concepts, maybe some other subject, some other senior teacher or one of us, or maybe you send us some queries where you want some master mentor tips and all. So with this, I'm signing off. Thank you. It was very nice talking to you all. Have a good day.